Hi, everyone. This is actually the second time I'll be giving a talk at JJI in a few weeks. So thank you so much to the organizers for organizing such a wonderful workshop that now ends in this conference. Um, I've been asked to report on the latest DESI results and explain or give an overview of what's coming next. So I may go a little fast-paced in the introduction also because to keep us on time, but yeah, let's get started. Let me see if I can do something about that. Sorry, it's such a fail. Okay. All right. Yes. Ooh. Right. So on one end, we had Lemaitre that proposed in the late 1920s that the universe was expanding at the same time that Edwin Hubble was making those observations. Later on, let's say 50 years ago, the expansion rate of the universe, H naught, was known to be between 50 and 100 kilometers per second per megaparsec, and that was the teams at the time. Now we've grouped the fight around 67 to 73, and so that's more or less our starting point as to what motivated to create a large-scale survey, spectroscopic survey of the sky, is to go towards addressing this question. All right. Sorry. No? Yeah. Okay. Yes. So the principle of how we paved the relationship between the distance that we measure and the redshift, and what allows us to measure H naught, so the expansion rate of the universe, started with Cepheids. So very locally, there's a relationship between the luminosity and the distance. So with photometry, we get the luminosity. With spectroscopy, we measure the redshift, and that allows us to constrain or to make a measurement of H naught. Great. So then a little bit later on, we push that reasoning, and we do that with exploding stars, and we're able to now cover a higher redshift range. And that's what gave rise to the Nobel Prize of 2011, where now populating this relationship, right, this Hubble diagram, what was measured was that the universe currently is expanding faster and faster. And so that's this accelerated expansion. And actually, Dragan, who was here last week, who gave a talk, reminded us that he, along with Mike Turner, were the people that came up with the term dark energy to rename I guess lambda constant as to include a range of other possible models, right? The cosmological constant. On top of that, from observations from the cosmic microwave backgrounds, you look at the temperature anisotropies, and that tells you things about the causality and the size of the universe in its first 3 minutes, let's say. And so putting information from the very early universe together with information from the very late universe, all these ingredients together create a framework for a cosmological models with observables that we're able to test. And they have successfully predicted over the past 20-ish years this cosmological model has successfully predicted those observations. Now we're pushing the limit lower, and like the precision higher and higher in terms of the measurements that we're able to do. We're making larger surveys, increasing the statistics. And so the question really is, with all of our different observables, are we still telling a consistent stories? Which again, and I'm gonna echo or at least point out different talks that you may want to see from previous weeks. We had at some point Rafael Busso, who came and gave a talk who addressed really what is it that we're trying to achieve, and if it's understanding the nature of what dark energy may be, it's one thing. If you're trying to see whether as a field we're able to build a consistent story, that's also a slightly different angling. And so depending what your motivation is, you may find some of the upcoming results of more or less interest or provocative. And so I'm really here to display these results, and I will let everyone then pitch in later on during the week. But with the standard model as we have it, we have essentially ingredients that are unknown. And dark matter, the skeleton of the universe, represents 27% of the full content. Dark energy, 68%. And another missing information that I'll touch on in this talk is the mass of neutrinos. So overall, 95% about of the content of the universe is a question mark to us, which then I think gives us an opportunity to actually pat ourselves on the back because you realize that the thing that we're doing is collecting photons, a very small amount of photons out of all of the photons that have ever been emitted. And we're still able, with that very little information from that very little content of the universe, to have derived a model, a framework, and paint a picture of the totality of it, which I think is still nice to sit back for 2 seconds and remember that this is what we're doing. Now, as far as model or what we're constraining, and one more word on the framework is Einstein's fields equation. And really, the relationship that you need to remember is that matter tells space-time how to curve, and curve space-time tells matter how to move. And so we're able to have access to how matter moves because we're taking snapshots at different moments of cosmic history, and we're seeing this evolution, and therefore we can learn about space-time and then really touch on the nature of, on relativity from this point. So I've talked about observables. I will focus on the observables that we are looking at with DESI. The main one, the first one, is the baryon acoustic oscillations. Very quickly, again, universe is expanding. You have a soup of primordial particles. They are bumping into each other. At some point, the universe expands enough that the photons decouple, they stop breaking up, proton and electrons forming the first, particles of hydrogen. And so that those oscillations stop and freeze in place. You have shells where you have the first atoms created that now only grow with the expansion of the universe. If this is where you have matter, right, on those overdensity of dark matter, then this is where you'll have eventually the largest structures get created and then be able to be observed. And so the size of that pattern just gets blown up as proportionally with the expansion of the universe. So when it gets created, it's 150 kiloparsec. Now what we're measuring in present time is 150 megaparsec. Right. And what it looks like in the slice is, at least can I use the, yeah. What it looks like in a slice is this overlapping pattern that you see in this blue hue. And schematically, we're giving galaxies and the intergalactic medium measurements of this pattern at redshift 0 to 2.5. We have input from the cosmic microwave background. We're measuring the 2-point correlation function. We want to know where this peak is. And that is, in very simple term, what we're trying to measure. Obviously, this was, integrated over distances, but really when you're trying to figure out where the peak is, there's two things. There's, when you're looking in 3D, there's the size across the sky and the size along the line of sight. And both of them, because of redshift, gets stretched differently. And so you actually make two measurements One is the size of that pattern in that direction and in this direction. And both of those combine and code the expansion history of the universe. And I did mention, depending on the effect of redshift or the Doppler effect. And that's because that's a systematic for it. But as with every systematic, there's valuable information encoded in it. And so with redshift space distortions, your simple picture that just has two galaxies, you measure the redshift, you do your correlation function, you have the monopole. Well, actually, if you account for peculiar velocities of galaxies and how they get enmeshed with the redshift measurements, they actually will affect the quadrupole, but they will also encode information about the growth of structures, and they will allow you to test gravity and dark energy, and also constrain additional cosmological parameters. So these are really the two main analyses that DESI, the dark energy spectroscoping instruments, has focused on measuring. And so now I will also take the time to thank, our sponsor mentioned that this is a very, very big endeavor that has over 70 institutions involved, over 1,000 people listed. It's been a lot of collaborative work. And that started actually with a photometric survey. And so I'm mentioning this because we took the data and we took data with 3 different telescopes and covered 18,000 square degree of the northern-ish sky. And that's important, and I'm pointing it out. You have access to it through the legacy viewer. That's where we did our target selection from, meaning picking what galaxies are going to be observed spectroscopically. But I'm mentioning this because DESI, in 2021, when we started, was announced as a 5-year survey. It is now an 8-year survey. There is no extension. We just crossed a number, and we're now an 8-year survey. And we're going to survey 17,500 square degrees. So taking advantage of most, if not all, of the imaging that we had done. So we're upgrading our plans compared to the start by 3,500 square degrees. And so that's where, when we were targeting, we started by targeting 35 million galaxies and redshifts of galaxies and quasars. Currently, we have measured about 40,000. And by the end of the survey, now in 2029, we'll have reached well over 50 million. And so out of the redshift and the galaxies that we're targeting, there's 4 different samples of interest. The bright galaxy survey at the lowest redshift, luminous red galaxies. So those samples overlap with the type of galaxies that we were looking at in SDSS. They're emission line galaxies, the ELGs, now plug in and extend the redshift coverage up to redshift 1.6. And finally, you have the quasars that bring us all the way up to for redshift 4. And we're also having a Milky Way survey. And something that's interesting is that the red zones that I'm highlighting now are the zones that will be observed in the next 3 years. And maybe the most interesting part about it is that they will increase our overlap with Rubin and Simon's Observatory by 50%, and they increase the total survey volume that DESI has collected in 5 years by 20%. And so those areas that are next on the observation plans will allow to interact with, all of you that are members of, overlapping community, whether you're doing weak lensing surveys or CMB surveys. One of the data points at high redshift comes from the Lima Alpha forest. I will just very quickly describe it because Matteo Viel, in the next couple of days, will be giving a talk on cosmology with the Lima Alpha forest. So I'll let him tell more about it. But essentially, we're using absorption features in quasar spectra to know and highlight where clouds of hydrogen are. we map out those clouds of hydrogen, and then we use their positions to, again, do statistical analysis as to where matter is at that redshift in the same way that we do with galaxies. Right. Okay, so DESI instrument located in the Northern Hemisphere at Kitt Peak National Observatory in Arizona. It's a 4-meter mirror on which we installed the DESI instrument, which is this black cylinder over there. You have the collecting area that is the 4-meter mirror. It's the twin of the Blanco, where the Dark Energy Survey has been operating. We have a system of lenses that then converge off that light on a focal plane that is a highly multiplex spectroscopic setup that has 5,000 optical fibers divided into 10 petals. Each fiber is glued to a little robot. Those robots dance and come and position themselves on a patch of the sky to match those galaxies that I was showing earlier that had been targeted. Great. And then they bring this light to each petal. So each set of 500 fibers gets brought up to one spectrograph. We have one spectrograph here that is blue, red, near infrared, covering basically the optical range and near infrared. And the reason that we are happy to have access to this range of wavelength is that for galaxies, and in particular emission line galaxies, our spectrographs allow us to resolve the O2 doublet, which then allows us to get confident redshifts for emission line galaxies. And for the Lyman alpha forest, we are sensitive in the blue enough that we can measure the Lyman alpha forest, which then gives us access to redshift 2 to 3.5. And so those extreme ranges, right, in the red and in the blue are what is actually helping us to complete this these measurements of the expansion rate or of the BAO feature at the highest redshift range that DESI reaches. So here, I wasn't exactly sure how to structure it because it would make more sense to start talking about our results from the baryon acoustic oscillation, the BAO measurement. But we have one with DR2, that's the first 3 years of data. The latest result from the full shape of the power spectrum is with DR1. So I'm just gonna give a quick word on how we're doing our full shape analysis with the latest results that came out earlier this year, that is with the first year of data. And then I'll move on to talk about the latest results now with BAO. So the first year of data, which is DR1, had about 128, so 1/3 of the entire footprint, the original 5-year footprint. It's still represented about 2 to 3 times more statistical, sample than SDSS had, and mainly located towards the equator. What are expected, so the DESI the constraints that DESI gets on gravity are placed now in comparison also to what was had with SDSS bus, I guess. So the squares are SDSS, the rounds are DESI measurements. The dashed line here gives you the prediction from general relativity, and what you're seeing is the growth of structure as a function of redshift. And so for smaller redshifts, so redshift below 1.5, DESI results have had a precision that's comparable to what SDSS had. However, at higher redshift, we're basically adding a finer grain of a redshift range in which we're making this measurements. And if we're projecting this here, you see again, general relativity is here, depending on what we're combining with of CMB, of BBN, of the weak lensing analysis from DES, we do find it to be consistent with general relativity. And another set of question was, okay, how does it do with dark energy? And this I'll address the next time. But if there's a couple things to keep in mind as far as the analysis that we're doing with the full shape in DESI, is that we have really two approaches that we're following. One is to do a full modeling for the cosmological inference, and another one is to do a compression. So the full modeling is just, let me just see, yes. It's a direct fitting approach by which you, given a set of cosmological parameters, you use your Boseman code, and then you just fit your resulting power spectrum to the data. And another way, which is to do the compression with the shape fit method. And here you focus on, you decompose your power spectrum in features, and you work on measuring and fitting those specific features. There's been comparisons that have been made as to which one performs the best and how complementary they are. And then the overall, modeling that you do, and this is why I'm not going to expand more, because Guido this afternoon will talk about EFT of LSS and go into more detail. But but the punchline is that full shape has so you can measure it independently. You make independent measurements, for each of the probes, which again populates. This is redshift range, so which are different snapshots at different redshifts, and you're finding you're constraining cosmological parameters at less precision than you do with BAO. But I guess more precision than you did with SDSS, and so that's still an improvement. And as far as the sigma 8 constraints, here it's regrettable I don't have the plot updated with the new kids results. But what's to remember is that, of course, sigma 8 is best constrained by weak lensing surveys, but with this method in DESI, we still find consistency with SDSS, agreement with CMB, and we, I guess, say no more than what has already been said on the tension, or at least the difference in measurement with weak lensing surveys. All right. Right, I'm trying to keep us on time. Now, as far as the baryon acoustic oscillation measurements, and this with the third year of data. So year one showed hint that, okay, let me rephrase. With year one, we had more statistical power than we've had with previous surveys. So now it becomes interesting to start simply fitting more models than just lambda CDM. When you do that, the other model that you have on shelf is this W0 time evolving dark energy. And your error bars have shrunk enough that now you can start differentiating this model from lambda CDM. And the year one results show that, yes, now we're able to do that. So how does DR2, which is 3 years of data, compare to DR1? Well, you're actually, again, increasing by a factor 2 to 3 the data sets, and you have 2/3 of the data collected. And again, we're working our way from the equator. We have blinded our data for the galaxy catalogs at the level of the catalog. So we've blinded the redshifts and the weights. And then we had a predetermined list of robustness tests that needed to be passed before we actually had access to the true redshift and weights. And that is all to prevent confirmation bias. For Lyman alpha forest, because you actually need the information held in each pixel, the blinding strategy was different, but as stringent. What's the takeaway is that as far as errors, where what still dominates is we're statistically limited, and that comes from survey volume and sampling density. So this is what contributes the most to the error budget that remains dominated by statistical error. Of course, for galaxy clustering, the dominant systematics, are different than that you get for the Lyman alpha clustering. And so, yes, you have the theoretical modeling, the galaxy halo models and connection that play the biggest part as far as galaxy clustering is concerned. As far as Lyman alpha forest, because really, what you care about for the BAO measurements is the position of the BAO peak. The nonlinear evolution of the BAO peak is what's the main systematic. Those systematics are not the same if you consider full shape measurements for one or the other, actually. Right. So now we have a big enough sample that we can slice it in 9. And so you have, again, lower redshift. So the way to read it is like this, and this is increasing redshifts. A novelty, I guess, with DESI is the combination of 2 different tracers, namely the luminous red galaxies at high redshift and the emission line galaxies at lower redshift. So that's a bin at about one redshift of 1.1 that give you combined constraints. And when you place that on this, Hubble diagram, so again, dashed is right. So dashed is going to be lambda CDM parametry. Yes. Flat is lambda CDM. Dashed is the time evolving WW naught model. And you see now where you can place all of those measurements. So, ELGs have been combined into one point for the purpose of that plot. Right. And the aggregate precision is 0.3, which is way below the 1% level. So that represents a big improvement in terms of constraining power from previous iteration of DESI and previous surveys. And now what's interesting to notice is that on this H0 omega m plot, you see that each individual tracer has degeneracy directions that are slightly different from each other, which is why the constraining power of all of those tracers put together is quite strong. Yes. So in the end, the measurements that you can make, that you can infer on cosmological parameters is that you find omega m at 0.3 and H0 and H0, HRD at about 101. And so that's DESI alone. Now, we've made claims as to how we are able to constrain other models in combination with other data sets. So let me just walk you through them. Right. So when I mention CMB here, CMB means Planck PR4 and ACT DR6. And so combining DESI DR1, combining DESI DR2 with CMB from Planck and ACT within in constraining lambda CDM it's consistent basically with the results that we had found in year one, which is those dashed lines here. And we measure basically still 2 sigma difference with CMB, which is perfectly fine. Now, when we're looking at our measurements of omega M and we compare it to different probes, so one still being the CMB, and then we differentiate between the different samples of supernovae, the idea being these are not our samples, we're just taking what's out there and comparing. So supernovae in general will find higher omega M. DESI finds lower than CMB, because I guess CMB is the reference here. But the tension, or at least the furthest away consistency is with the supernovae samples at different levels, depending on which one we're considering. Okay, so this is still within lambda CDM. As far as the fits, another way again to see it is BAO gives you quite large round constraints on the omega M H naught plan. You can break this by combining with CMB, and then supernovae stands there at the edge. And now, yes, okay. A little bit, just again, hammering the point is that lower redshift, higher redshift, you see a high level of consistency between all of the CMB surveys in terms of value centered at 67.5. Here is where, the BAO and combined with CMB is also hidden. And so you have this level of consistency. Then you have all of the late time universe probes, which are supernovae, tip of the right giant branch, Tully-Fisher relationship, and all of that good stuff that is centered in 73, at H0 73. So now, how do we tell a consistent story with this is the question as a community. From a DESI-centered view, the way that you start going about it is that you, given that the BAO also measures omega M, and you make an assumption on the neutrino mass, then adding a BBN allows you to break the degeneracy and make this measurement. So that's the first thing. So you have an H0 measurement from BAO combined with BBN that's independent from CMB. So are the two then still consistent? Yes, they are. You see a bigger tension with shoes. That's the most extreme case of tension in the supernovae, which is why it's the one that we put here. Great. Now, as far as parametrization of dark energy that we're testing against, it's the CPL, right? The Chevalier-Polaski-Linder parametrization that we are now expanding and adding to testing on top of lambda CDM. And that's this W naught. So in the two directions that you're measuring your BAO feature, the one dashed line is still lambda CDM. And then if you allow for this other parametrization, you see how you measure, I guess, the WA parameter that would be 0 in case of lambda CDM, and if left free, you see how it evolves with redshift. Right. So then, now that you're allowing for it, does it change? Do we still find lambda CDM? The answer is with DESI DR1, we found the dashed contour that said we're consistent with lambda CDM if you allow a bigger, like a fitting that allows for additional variation in the equation of state, then we're taking it. And there's actually also consistency with this time-evolving dark energy. Now, the question was, well, if you throw in 2 more years of data, do you still find similarly? And the answer is yes. You're still consistent with cosmological constant, but you also allow for this possibility of time-evolving dark energy. But your consistency with lambda CDM is 2 sigma. Fine. Yeah. This is just DESI now. I'm really like deconstructing it, and I'll come to the bigger claims in a second. Now, if you add CMB to just DESI, you see that you're like compared to year 1, you're now moving away from at least in the 1 sigma contour, moving away from the cosmological constant. So, and there's a 3.1 preference for time-evolving dark energy. Okay, so these are the 2 high redshift probes combined. Now, what do we find if we now add the various supernovae sample? So we're doing them one by one. That's DESI, DR2, CMB, PR4, and ACT, and each of the supernova sample available. And you see a continuity in that shift slightly away from the cosmological constant at different levels of confidence. And so really you see that adding the supernova sample is what pushes over the edge, I guess, the claims that there is a stronger hint for the possibility of time-evolving dark energy. So how robust are those claims, if you want to call them that, or just observations on models that you've been testing? Well, if you fiddle with the CMB data and includes just the anisotropies without the lensing, or change the priors, does that significantly change when you combine just DESI Year 2 with just those CMB data that have been curated? And you see the evolution of those contours, and there's a weaker preference, but it's still very similar to what I had shown before. That was all the CMB inputs combined. Okay, so now you take this and you add and you replace the CMB with the weak lensing constraints from DES Year 3, the 3x2, and you see that whether you, right, and DESI R5 is, I believe, yeah, DESI, right, in galaxy clustering, okay. And so you see that the constraints are not as strong or not as further away from lambda CDM, which would be here. But there is a clear preference for the same region. So at least it's all trending the same way. So if I summarize a bit, whether you're looking, looking here, for example, at just the isotropic BAO distance measurement, the lambda CDM model can feed DESI BAO, sure, no problem. It also can feed DESI plus CMB, even though the preference, is less, like the consistency is a little bit less, but it's still perfectly consistent. Really, what happens is that if you now add the supernovae, and you still want to be able to tell the same story when you add CMB, galaxy clustering from DESI, and supernovae, that's where the story breaks down, and that's where supernovae alone can be fitted by lambda CDM, but not all 3 simultaneously. So this is really the observations that DESI is making. However, now you say, okay, let me try another model instead of lambda CDM. If I put this WA, W naught parameterization, can I tell a consistent story where if I believe that all the measurements that I'm taking are robust and not too touched and nothing is left to do, is there another model that would give me a consistent story when I put them all together? considering they're all coming from the same, universe. And that's where you see that time evolving dark energy, so this W naught parametrization allows you to have all three, so CMB, MBO, and supernovae together. So again, these are the claims and the observations that are coming out of the DR2 BAO DESI papers. And here, I'll just highlight because the full shape from DR2 will be coming early next year. But in the meantime, I just wanted to also remind and just keep in mind what we had found when adding full shape to the BAO of DESI DR1, whether that we were telling the same story with this. And the short answer is yes. So I'll just show you this evolution if depending on what supernovae sample you combine with, still, CMB is the same. And the takeaway is that full shape adds adds information. We get slightly better constraints in the W naught case. And you see the same preference for the same space. And it's of the similar significance that lambda CDM versus time evolving was in DR1. We'll see whether that statement holds true or changes, and in which aspects when we have the DR2 results. In the interest of time, I'm actually gonna skip maybe some of this just to say that if we're looking at the measurements in the case of time evolving dark energy, what we're really finding is that the acceleration would start sooner. We're observing an acceleration that starts sooner than it would have if we were living in lambda CDM, and that 2 days acceleration, while it's still accelerating, it's not accelerating quite as strong as it would be if it was in lambda CDM. So if there's a worthy idea to remember as to what the implications are if you consider this model, this is it. Right. Now, just a word also that we're not just constraining dark energy, we've also looked at neutrino mass and okay. And in lambda CDM, so BAO breaks the degeneracy quite well, and it's the tightest constraint to date if you consider lambda CDM. With the one caveat that there's a preference for negative neutrino mass. So I will let you, well, I know like we've had a few discussions in the past few weeks at the workshop on this, and I'm, curious to see what the inputs in this room are gonna be later on during the week. However, we'll also note that if you now consider W naught, you're relaxing your constraints, and then it's same ballpark as previous surveys have considered. So, right. Now, what comes after DESI? I've already mentioned that we're going to end DESI in 2029. That will have provided and increased the overlap with Rubin and Simon's Observatory by quite a lot. But it's not done. Once DESI finishes, there will be a 6 months period where there will be minimal instrumental upgrades and maintenance. And then we will be using the same instrument, and we will actually start a new program, hopefully, that we call DESI 2. Two different orthograph, but it's actually DESI 2 with the Arab 2 over there. And it has different science goals, very different science goals than the nominal DESI survey. And so we'll have a high redshift galaxy program where we'll focus on tracers that are Lyman break galaxies and Lyman alpha emitters. We'll have a high density galaxy redshift survey at lower redshift. We'll have a Milky Way survey and And there's a lot of other things that can be done with the data that we'll provide. Something to note is that it's really science as a pathfinder for the future generation of spectroscopic surveys. And I'm saying this because the targeted, or at least the hoped survey volume, like a square footage for the high redshift galaxy survey is about 1,000 square degrees. So really think of it as a pathfinder for future spectroscopic survey. And just to give an overview, I presented this last summer and at a workshop in Split. And actually, there's been quite a lot of changes. Here was CMBS4. It is not there anymore. Certain surveys have moved to their starting point, and others have indeed started since then, which is great. Oh, okay, yes, something got deleted here. But really the point is, so DESI will be immediately followed by DESI 2. In the meantime, PFS, that is the prime focus spectrograph, that is really cool in the sense that they have much better sensitivity in the blue, will also be ongoing. Weave is, and Foremost, that's the one that's missing. So Weave and Foremost that are European multiplex spectroscopic surveys. So one is ongoing, one should start commissioning very, very soon. SphereX has been in space for about 6 months now. Roman is coming. Euclid has been up there. Rubin started, and what you see here, DESI2 IBIS, is the imaging survey that we are that is in progress for the targeting of DESI2. And as many of you might know, it's not trivial to be able to have a full catalog of Lyman Break galaxies and Lyman alpha emitters for us to be able to do target selection for DESI2. And so these are the efforts that are ongoing, and that's also the reason why DESI2, the high redshift program, will focus on a concentrated area with the hope of expanding for SPEC S5, the WST, Wide Spectroscopic Telescope, I think, and MUST, that is the Chinese counter. So basically, Americans, Europeans, Chinese are all those highly multiplexed, 20 to 40 fibers on sky, bigger mirrors, or a telescope in the north, a telescope in the south, different configurations, but it's just the next level ambitious programs for multiplex spectroscopy. And then Simon's Observatory is now really confirmed to then be the next big thing for decades, with the advanced SO coming up as well. And so that gives you admittedly probably still somewhat biased and incomplete picture of all of the surveys that we will be lucky to work with in the next decade, but you can keep that in mind. And so as far as what we're trying to do, people may disagree on what the actual question we're trying to answer. I do think something that's interesting is focusing on what we are able to do rather before anything else, which is, are we able to give a consistent story? And if not, why? Right now, the measurements we've done, something has to give, or something needs to be understood, and I think that's really exciting. And then again, something I'm very excited about is the overlap we'll have with Rubin and SO in the next 5 years, because that will enable a lot of really cool science cases. I know I already gave that talk like two weeks ago with a little bit less stuff, so yeah. Yes, these are the possibilities. Um, like I said, I think that like my personal opinion is that now we're getting to levels of precisions where we can start testing more models, right? That's interesting. Um, there as many people in the room, as many models you can come up with, whether they match reality. It's a very hard thing to follow and figure out. Um, I think the most like the way at least the question that I think is most interesting is, are we able to tell a consistent story from the uh, point of putting together the measurements that we've made? And so in terms of the highest priority of things to look at, I think is to check for systematics before, I mean, definitely test as many models as you want, but having conclusions as to which model is the best only comes once you have an ironclad level of confidence in one, each of your individual measurements, two, how you combine those measurements. What explosion factor? Okay, so there's so two different things. There's give me 1 second. All right, so if you look from here to there, I don't no, right? That's just the number of passes, okay? And then give me one more second. This? Yes. Basically, we're not changing the location of the telescope. So at the edges, um, here and there, you just have a much higher air mass. So you need to go through more of the, yes. So it adds additional things to factor in, which, you know, we went for the easiest part, which is basically straight up. And then now we're eating away at the footprints on the side, and that adds more air mass and more considerations. But we've been doing testing for that for already like 2.5, 3 years. And so this is, yes, it's just more time consuming. It will be just as successful. Yes, yes. Yeah, so basically to have your survey, to add to your survey in the same level of homogeneity and like, you know, consistency, you just need, you have additional time on sky, which means slightly, ever so slightly changing a little bit some of the details of the observations to get the same effective time. Um, Well, you'll hear about it from a bunch of people that are presenting ACT results. But for example, if you do, well, I see Noah laughing, but he's talked about cross correlation between DESI samples and CMB lensing. And because you have really good localization of the galaxy samples, that allows you to take advantage of the information that you have from CMB lensing, but localize them well in certain redshift. You can also do kinematic Suniel-Zeldovich, so the KSZ measurements that you may have heard of. And I'll let the CMB people in the room tell you why they're excited about it. But at least there's been in the past year and a half, 2 years, a lot of interesting science that's come up from this overlap with ACT and DESI.